So welcome and thank you for coming to today's lab. So this is our very first lab. In this first lab, we're just going to simply work over a voltage divider, look at a couple of different components, a photoresistor and this thermistor, and learn how to make some basic measurements. I'm going to point out the differences between the lab manual and what it says to do, and a few things that I'm going to do differently for this specific lab. Alright, so let's go ahead and get started. So in this laboratory procedure, we're going to first do steps A through F. In other words, section 1.3 of the laboratory procedure. So what this procedure is going to have us do is take two resistors and a power supply and construct the circuit that is in figure 1.1D, which is a simple voltage divider. It composes of a 5-volt power supply, a 100 ohm resistor, and a 220 ohm resistor, which we have here. This is a digital multimeter here that we're going to use to measure the resistance and also to measure the voltages. And I'm going to demonstrate how you use a digital multimeter to do this. Specifically why I am not using the analog discovery, even though I do have one here, is we're going to use the analog discovery in other labs. But I wanted to specifically demonstrate using the multimeter in this function because this is a simple DC circuit, and given that this is a class for non-electrical engineers, the most predominant thing that you're going to use in your career as a tool is going to be a digital multimeter. So I want to make sure you see switching between the different modes and the different ranges on the multimeter and what it means. So that's what we're going to focus on today. So this is a really simple circuit, and we're going to go through some processes. I'm going to tell you what the measurements are. And so let's review the steps. So for step one, we just simply take the two resistors that we have, which is a 100 ohm and a 220 ohm resistor. We're going to create the circuit in step two, or part B, and then we're going to hook up the power supply. We're going to measure the power supply. I'm going to turn on the power supply. We're going to measure the power supply, what the nominal voltage is, and then we're supposed to then, of course, before all of this, we're supposed to measure the actual resistance values because as you'll see in the chart for the resistor values, these resistors have a tolerance. Even though it's 100 ohms, these are what they call 5% resistors, meaning that the actual value is within plus or minus 5% of the rated value. In this case, we have a 100 ohm resistor, so it could be 105 ohms, or it could be 95 ohms, or something in between. So nominally it would be 100 ohms. Same thing would be for the 220 ohm resistor. So you would end up with plus or minus 5% of that. So we're going to measure the resistances, jot that down in our lab notebook of what the actual value is. What you need to do is you're going to have on part D, you're going to record what you calculated the resistance values to be for V1 and V2 using these actual measured values. So you're going to take the equations and the data that you figured out for the pre-lab using the 100 and 220 ohm resistor and the actual power supply. In other words, you figured this out for 5 volts, 100 ohms, and 220 ohms. Now you're going to take the actual values that we're going to determine and actually measure, and you're going to calculate what it's supposed to be with these measured values. And then you're going to compare that to what my measurements say is for V1 and V2. And that's going to be, and then you've got to come up with a percentage difference. So in the lab report, you're going to have the fact that this circuit was created. You're going to jot down the differences that I used a multimeter and not the analog discovery module, what the actual resistances was, what the actual power supply voltage was, what VS is, and then what V1 and V2 actually were, and then you're going to compare that to what you calculated the values to be based upon this data. So let's just go ahead and get started. So first things first, we need a power supply. So like I said, in this particular lab, I'm not going to be using the analog discovery. I am going to be using an external power supply. And so for this, I'm using this Tech Power multi-channel power supply here. So we're going to simply turn it on. And so we have 4 channels. And I'm going to go ahead, I'm using channel 2. I've got that configured here. So I'm displaying channel 2. And I'm going to go ahead and set, I'm going to turn on the output and I'm going to set 5 volts. So it was default to 24 volts. So it's always important before you actually apply power to your circuit. Notice there's no wires connected to anything right now. So we're going to go ahead and adjust this down to 5 volts. We're going to set the current knob. If I set the current to 0, that means that no current is going to be allowed. This is called the current limit. We're going to go ahead and allow current to flow. So right now there is 5 volts on this terminal. So we got positive and negative terminals on this power supply, this terminal right here. So right now it's nominally set to 5 volts. There's no current being pulled, and we have 5 volts here. I'm going to go ahead and turn off the power. Notice it goes to 0. And we're going to go ahead and hook up our terminals for that. Alrighty, so here's our terminals. Go ahead and connect these. So we've got our negative and our positive leads. So we come over here, and we're going to go ahead and connect the negative to this ground, and we're going to use the red here for our plus and minus, plus 5 volts and ground. So there's our connectivity. All right, so the first thing is we're supposed to measure the resistance values of both the 100 and the 220 ohm. So what we're going to do is we're going to turn our digital multimeter here to the ohm mode to measure resistance, which is this right here. So we're now able to measure resistance, and we're going to start with the 100 ohm resistor. The 100 ohm resistor has a brown, a black, and a brown band. So if looking at the chart here, we can see that we have a 1, 0, 1 with the significant figures. Or in this case, we have 1, 0 for the significant figures, and then we have a 1 band for the multiplier. So again, just to say again, we have a brown, a black, and a brown, which means we have 1, 0 as significant figures and a multiplier of 10, giving us 100 ohms. So, with that being said, let's go ahead and measure this resistor. So we connect both of the terminals like this, and we measure 98.0 ohms. So this resistor is not 100 ohms perfectly, it is 98.0. Now it's 97.9. So let's take a look again. Let's do another reading. 97.9. So the resistance for the 100 ohm resistor is actually 97.9 ohms. So we have that. So that's resistor 1. The next resistor is the 220 ohms. Similarly, it has a red and a red band. So we have 2 red bands for the significant figures, and it as well has a brown band for the multiplier, giving us 220. So let's take a measurement there and see what we have. Here we have 218.1 ohms. So this resistor is 0.1, now it's 218 even. So it kind of did the same thing, went down 0.1 ohms. So 218 ohms. So our 2 resistors are 97.9 and 218. So let's go ahead and write that down. R1, which is supposed to be the 100 ohm, actually was 97.9 ohms, and R2 is actually 220 ohms, or was, and it's actually 218 ohms. So now we need to build the circuit that is shown in 1.19, which is simply a power supply, the 100 ohm resistor, and the 220 ohm resistor. So let's go ahead and do that. So we're going to go ahead and turn off our multimeter. This multimeter here, if you leave it on for a while, will beep at you, so it can conserve battery. So we have 2 wires here, a red and a black wire, and we're going to connect one to VA, which is our plus 5 volts, and currently the power supply is off, and so we're just going to connect that up, and we're going to connect the other one up to our ground return, so R0, our reference node, if you will. So we've got our plus or minus 5 volts, and on the breadboard you'll notice that we have these rows and columns, and the rows are actually shorted together. So if you can see this, and I'll take in a screenshot here so that you can actually get a really close-in view. So how a breadboard works is this row is shorted together. So as you can see, we have A through E is all shorted together, and then F through J is all shorted together. Each row is separate. So if I put the 5 volts in here, let me get that to focus for us. I'll go ahead and put that in. That would provide 5 volts to this, and then we could put in the ground over here for part A. So that would give us our plus or minus, give our 5 volts here. So let's go ahead and finish out the rest of the circuit. So we have a 100 ohm resistor that goes first. So let's go ahead and do that. So let me get this a little more in position so you can see this. Actually, I'm going to adjust this down a little bit so we can see this a little bit better. So let's go ahead and put our 100 ohm resistor in. So that gives us 5 volts. So we're going from the positive 5 volts to the through the 100 ohm resistor. So we have that. But now we need to return this back to ground. So this is the 220 ohm resistor. And so what we're going to do is go from here over here. And that's our 220 ohm. And we'll go ahead and connect ground here. So a little bit of a zoomed in view. We have the 5 volts coming in here. It goes through the 100 ohm resistor, crosses over to the 220 here, goes through the 220 ohm and back out to ground. All right, so now that we have the circuit created, now we're going to actually connect up some power and measure. So let's go ahead and hook up our power supply again. So let's go ahead now that we have this power supply all connected. We've got the resistors configured in circuit. Let's go ahead now and apply power. So we're going to go ahead and turn on the power supply. And we go ahead and do that here. So notice it's currently 0. Let's go ahead and apply power. Now we have 5 volts. It is taking a little bit of current, which shows that we actually have the circuit connected. So now we need to measure the voltages across this. So as per the lab manual, you're supposed to now use the values we have, and you're going to calculate what the voltage drop should be across resistor 1 and 2. So first things first, let's measure what our 5 volt power supply really is. So we're going to put the digital multimeter on voltage mode, DC, and we're going to measure the voltage. So we're going to do it two different places. We're going to do it as it enters the board and then actually across it. So what do we have here? We have 5.009 volts right there. And then right here at the terminals of the resistor, so actually on the breadboard itself, we're measuring 5.001. So this is the value we're going to rely on because this is without any resistance drop, any voltage loss across the wires, and this is straight on the breadboard itself right at the terminals of the resistor. So 5.001 volts. So we're going to say Vs is equal to 5.001 volts DC. So we have that. Now we're asked to measure the voltage drop with the circuit on across resistor 1. So let's do that. And we have 1.54849, so you probably could say 1.549 volts across the 100 ohm resistor, and that is V1. So again, one more time, in the correct direction, notice the red and the black here. So red being positive, black being negative. 1.549 volts. So V1 is equal to 1.549 volts DC. Now we need to measure V2, which is simply the voltage drop across the 220 ohm resistor in the same direction. So again, positive, negative across the 220. We have 3.449 volts. So V2 is 3.449 volts. So let's write that down. V2 is equal to 3.449 volts DC. Now, just out of curiosity, those two numbers added together should equal what? It should equal 5 volts. So it's a voltage divider. 1.549, 3.449, add them together, and we get 4.998. So we're losing a couple millivolts, probably in the losses of the internal parts of the breadboard, which is to be expected, actually. So again, I'm going to go through all this again one more time just to say I did. We have a power supply of roughly 5.001 volts. V1 is 1.549, and V2 is 3.448. And a moment ago, we measured 449 volts. So that is exercise 1.3 of the lab manual. So now we're going to do exercise 1.4, which is using the photoresistor and the thermistor. So our first part here is to measure the resistance of the photoresistor when exposed to ambient light. So we're supposed to cover the photoresistor with cardstock for about a half inch above the surface, and then measure the resistance, and then shine a flashlight on and onto the surface and record the results. So there's 3 resistance measurements we're going to do. So first thing, I need to show you what a photoresistor looks like. And so here we have the photoresistor. I'll give you a close-in view here in a second. So that is the photoresistor. The photoresistor changes its resistance based upon photons, based upon light. So let's go ahead and plug it in the breadboard here. So we're not going to hook it up into anything just yet. We're just going to plug it into the breadboard. We're going to change our multimeter into ohms. So we're going to measure resistance. And now we are asked to come up with 3 resistance values. So we have covered, so we have the photoresistor. So I'm putting in my lab notebook, or I'm doing this on a sheet of paper, but in your lab notebook you would write this down. So we have photoresistor, we have covered with cardstock. We have ambient light. And then we have flashlight. So we have 3 values we're going to do. And I have a flashlight, I have cardstock, and we have a photoresistor. So first things first, let's go ahead and get my probes on the photoresistor. And then we're going to cover it 1/2 inch above approximately. So, oops. So let's go ahead and get that in position. So put it about 1/2 inch above. So we have about 20, see if you see it changing. We have probably, I'd say, 21.5 K. Probably a good number. As you probably can use any of these numbers that are being on the screen, but let's just say for purposes of argument, this is about 21.5 K, because it really is changing just me holding it here. I mean, as I give it away, you notice the brighter it is, it gets less resistance. So I'd say about, let's get this in position, get a good contact on the thing. Let's see. Yeah, 20, anywhere between 22K. So just take whatever reading you want in here, because this is all valid, because I'm hand holding this. This is not precise. So I'm going to call it 21.5 kiloohms. Mine, I'm going to call 21.5 kiloohms covered. Now, ambient light. That is the light in my lab here. We have 9.65 kiloohms. And as you can see, it's fluctuating, because as you would imagine, light's kind of fluctuating around a little bit. Now it seems to have steadied out at about 9.76K. So 9.76K. Now, let's just ask ourselves a little mental exercise here. If I apply a flashlight, what do you think is going to happen? Is the resistance going to go higher, or is the resistance going to go lower? I'm willing to bet the resistance is going to go lower. because as we saw, we covered it, we had higher resistance. In fact, I'm wondering, the lab experiments had here about 1/2 inch or so. So I'm actually going to completely cover it. So now you notice it's a little bit different just in the room. I'm flat out going to go ahead and completely cover. And as you can see, completely covered is about 40K. So we've got covered. We had about 21.5K. Now it's running about 10K, open. So now I'm going to apply a flashlight. So what do you think this is going to be? I'm thinking the resistance is going to go drastically decrease. So let me go ahead and connect my probes here. I'm going to turn on my flashlight. I'm going to actually use a beam, and I'm going to completely shine right on top of that photoresistor. And as you can imagine, the closer I get, the less resistance. So I'm going to hold it right about here, and we're going to call this, we're just going to pick a number here. I'm going to call this about 3K, 3 kilo ohms. So anything you see on the screen here you can use. These are all valid values, because as I change the position of the flashlight and change the angle by which it hits, obviously the light intensity changes, and hence the resistance value changes. So we could call it 3K, we call it 3.2K. So there's strobe. I'm sure that was great. So let's just get this in position. See, now we're getting into the low ohms. So completely exposed, we're looking like about, right now, 560 ohms. So I'm just going to go with that. So we're going to turn this away, and it's going back, shining light on it. We're getting about, this is about 450 ohms. So that's what I'm going to write down, 450 ohms. Doesn't have to be exactly precise because there's so many variables here. Just the way I'm holding this changes it. And depending on the angle by which I come in, what I'm done differently here is I'm actually coming on the angle. I'm probably perpendicular to the surface of this photoresistor. And by doing that, I got more photons into the photoresistor itself, and it is changing. So as I get closer, it's less and less. Further away, you can see it changing. Take the flashlight away, and you can see it's returning back to its normal ambient value. Bring the flashlight. Notice how quickly it responds. So I'm going to say my measurement's about 450 ohms, but you obviously can take whatever value you're seeing here. Okay, so we have that. So we've recorded those values. So that we've done that, so we have, so now you've seen all these different effects of the photoresistor here. So now you're supposed to give us, in your report, you're going to give us a couple sentences as to what you think is happening, obviously to the resistance based upon light. So it's pretty obvious what's happening. We went from completely covered, being close to almost 50 kiloohms, we having about 21.5 kiloohms with about a 1/2 inch up above the surface of the photoresistor. Ambient light in this lab was about 9.7 kiloohms, and then when we actually flooded the thing with a flashlight, we were getting resistances even below 450 ohms, but somewhere in the neighborhood of hundreds of ohms for sure. So we said it was flashlight directly on the photoresistor, we had 450 ohms. So give us a couple sentences on to what that's be. That's part B. So we now measured of all these resistances, and you've given us a statement. So now we're actually going to use our thumb resistor. So what I've done already here is I have replaced R1 with a 10 kilo ohm resistor. So let's go ahead and measure this resistance. So I'm going to disconnect to 5 volts for the moment, and we're going to go ahead and put our ohm meter on. And the resistance is 9.83K. So this 10 kilo ohm resistor is actually a 9.83 kilo ohms. It's always good to take measurement readings of this. So 9.83 kilo ohms. So now we've actually measured these resistances a moment ago, and now we're actually going to measure voltages across. So we've created the circuit to use the photoresistor. So like I've talked about previously, and you're going to see this also with the temperature one in a moment, with the thermistor, this is why you study this course. In this case, we're measuring light. You might be in a photonics application where you need a light measurement. Well, this is a simple circuit that you would use in conjunction with an analog to digital converter and a computer. You can actually measure light and calibrate a circuit based upon a light intensity, or as in the circuit that we're going to show in just a moment, temperature. So let's go ahead and finish off part C here. So we've recreated the circuit with the 10K resistor, and now we've replaced R2 with this thermistor. And now we are going to measure the voltages across the thermistor. So we put ourselves into voltage mode here. And we're going to go ahead and measure voltage now instead of resistance. So let's go ahead and make the circuit live. So we got 5 volts across. So let's just, for the sake of measurement, let's take a look at our measurement again. This time we're running about 5.011 volts. So make a measurement of that. So Vs now is equal to 5.011 volts. Voltage does change a little bit with temperature and just the way the room is. So if we had 5 volts. And now with ambient light, we're getting about 2.16 volts. So the first thing we're asked to do is measure what is the voltage with the covered cardstock. So let's do this in order. So roughly about a half inch above, we got about 3.8, we'll call it 3.8, it's kind of decreasing, let me drop this back down, 3.8, we'll just call it 3.8 volts. That's just what we're going to call this. So the voltage across the covered cardstock is 3.8 volts. Of course, you could use any of the voltages that you saw displayed there. Now we're going to get the ambient reading. So ambient, just the light in the room, is approximately 2.336. So ambient, 2.33, now it's reading about 2.338 volts DC. And then, of course, now it's going to be, what is it with the flashlight? And we saw we got a lot of different readings. So now that we're decreasing the resistance here, the voltage is clearly doing something. It's going down as we increase the light. It was 3.8 volts. Now it's 2.38. Now we added the light on there, and the voltage is now 292 millivolts. Notice the change, and 290, so 0.285280 volts. Notice the change in the units. So I take the flashlight away and went back. Volts is an auto-ranging digital multimeter, so 2.5 volts. Put the flashlight back on, and now we're reading about 300 or so millivolts, depending on the angle of my flashlight and how I hit this. So I'm just going to call it an even 250 millivolts. So flashlight, approximately equal to 250 millivolts. So part D here, you're supposed to use these results, and you need to give us a couple sentences as to what you've observed here, what you see this circuit doing. So what is the photoresistor doing with the light changing? So is the voltage going up and down, etc.? Is there a relationship? So on and so forth. Alrighty. So now we're going to do section 1.42, which is the thermistor. So similar to the photoresistor, this is actually a sensing element. As you can probably infer by the name, this has to do with temperature. And so what we're going to do is we're going to take this thermistor here, which looks this little black epoxy body, looks a little bit like a capacitor actually, which we're going to talk about here in about a couple weeks. But this little device measures temperature. And so for the first thing we're doing is going to ask to measure the resistance across the terminals of the thermistor with ambient, in other words, standard room temperature, and then with our fingers rubbed. So I'm just going to put it in the board here just to make it a little bit easy to read. So, or into the breadboard. And we're going to go ahead and read the values here. So we're going to connect that up and see what we get. So room temperature, so put this on resistance mode. And we have about 8.84 K ambient temperature. So ambient for thermistor is equal to 8.82 kiloohms. So let's go ahead and do that one more time. Just say we did. It's probably going to be a little different. This time it's 9.22 K. So write down the value you think that's appropriate. As the temperature of the room changes a little bit, as the temperature around the thermistor changes, the resistance changes. Now we're getting about 9.06 K. I'm going to go ahead and write that down as well. All these values are correct. Now we're supposed to rub between our palms the resistor and just basically get this resistor nice and warm. So let's go ahead and do that. I'm going to keep the resistor nice and warm here. And then we're going to go ahead and measure this value. And now the resistance has gone down. And I'm pinching the resistor between my fingers to get a good reading. I think the idea is if you were doing this as a pair in the lab, it'd probably be a lot easier because someone could take the measurement and take the measurement reading while the other person is holding it. So this is a little bit tricky doing this as one person. You've got to kind of contort your fingers to kind of keep this between your fingers or something. So we got about 6.02 kiloohms. Actually, it's dropping. So 6 kiloohms seems to have steadied out at 6 kiloohms even. So we're going to call this finger temperature. We got 6.00 kiloohms. So he only had 2 data points here. So we had roughly 9 kiloohms. So we had one reading of 8.82 kiloohms and another reading of 9.06 kiloohms for the ambient temperature. And then the rub between palms, or really in this case between my fingers, kind of warmed up. We got a reading of 6 kiloohms even. So give us a couple sentences for part B here. Give us a couple sentences of what you observed. What do you think is going on? Is there a relationship between temperature and resistance, so on and so forth. So now we're going to be using the same circuit that we had a moment ago. We have this 5 volts here. I'm going to just connect that real quick. We got the 10 kilo ohm resistor, same thing we've had before. And now we're going to, instead of the photoresistor, we're going to put the thermistor in its place. So we'll go ahead and do that. Connect the 5 volts back up. And so now we can actually take a look at now voltage readings. So I'm going to go back into voltage mode. And we're going to do the same thing again with the temperatures. This time we're going to be measuring voltages. So let's go ahead and do that. And we're going to be measuring the voltages across the thermistor. So in this case, ambient room temperature, we got 2.42, now 2.4 is dropping because the air conditioner just turned on a little bit. Got some airflow in the room. Seems like it's steadying out about 2.37. We're just going to call it 2.37 volts. So ambient equaled 2.37 volts DC. Now we're going to kind of heat it up and take another reading. So I'm going to do my best to kind of do that. Use one hand to hold the value and kind of put my finger on it and see what happens. Well, lo and behold, the voltage is dropping. So we'll just kind of keep it there for a few moments, let this voltage kind of settle out. So now we have a temperature reading, or with the temperature, with my fingers on the thermistor, the voltage seems to have steadied out at 1.922 volts. Again, that's 1.922 volts. That's what we're going to use. So the warm temperature is equal to 1.922 volts DC. So now you're supposed to give us a statement as to what you observed here. So now the voltage clearly decreased upon changing the temperature. So you would write a relationship on that. So now part E of this circuit, so this circuit and the circuit before, both of these obviously values are a variable resistor. The resistance change is based upon some sensory element. In the case of the photoresistance light, case of thermistor, temperature. So give us a brief description of where do you think these could be used for. Maybe make it applicable to what engineering studies that you're currently doing. Like if you're in civil engineering, you're going to measure temperature, say, of a concrete pour or something. I don't know. Just pick something, and give us a where this would be useful in your field of study. And for instance, for light, what would you measure light for, and how this would be done? How would you use this circuit for that process? Well, that concludes this lab today. Again, the pre-lab is due on June 2nd, and the post-lab is due 1 week from that on June 9th. Both of them are due at 11:59 p.m. So if you have any questions regarding the lab, you can email me directly, or you can also discuss with your TA regarding the lab setup. Also, in your lab report, make note of the fact that I used a digital multimeter and not the analog Discovery 2 for this. Again, the purpose for doing this is showing you using the DMM for this particular application.